So logarithmic mean temperature difference or LMTD for a parallel flow. Here we will be having coaxial tubes like this, and we will be passing the hot fluid here. So hot fluid will be entering with the temperature TH1, and we will be passing cold fluid here, that is in the outer tube, with the temperature TC1. This is cold one. So what happens is, when it reaches the other side, a part of heat from the hot fluid will be absorbed by the cold fluid, such that the temperature of the cold fluid changes to TC2 and of hot fluid changes to TH2. So the one of the equation to be remembered is Q is the heat absorbed. It is equal to UA theta m. UA theta m means where U is the heat transfer coefficient. So we have something like Q is equal to HA delta T. It is something similar to that. Q is equal to U, overall heat transfer coefficient. A, area, there delta T is change in temperature. Here theta m is LMTD. And that's what we are going to define. What is the theta m? So what happens is, suppose say that a mass mh is the hot fluid mass that is flowing through the inner tube, and a mass mc is the cold fluid mass that is passing through the outer tube. Then for a small area, somewhere here we are considering a small area, and for a small area, suppose say that through that small area the cold body is absorbing a heat. So we know Q is equal to, so if the mass of cold fluid is mc and specific heat is cc, we know Q is equal to mc delta T or mc dt. That means if we are having a cold fluid, if we are having a fluid, and if it is having a mass m, and if it is having a specific heat c, and if the temperature change after absorbing heat is delta T, it absorbs a heat and there is a temperature change delta T, then the heat absorbed is mc delta T. So here for the cold fluid, to denote it is cold fluid, we are giving a subscript C. So if mass is m, mc, and specific heat is cc, say that temperature change for the cold fluid is dTc, then the mass absorbed, the heat absorbed by the cold body is dq, mc, cc, dt. So from that, this dTc is put in one side and mccc is taken to the other side. So we will get an equation. Now heat release, so this heat absorbed by the cold body is the same amount of heat that is released by the hot body. So heat released by the hot body is dq is equal to, again instead of mc there is mh, instead of cc there is ch, instead of dtc there is dth. And this negative symbol comes because dTh is actually the change in temperature. For a hot body, the change in temperature will be negative because it is releasing heat. So there will be a reduction of change in temperature. So in order to denote that, we are putting a negative. So and also here we have to look that this is a parallel flow. So when the flow happens from this side to that side, say this is the left side and this is the right side. So at the right side, the temperature of the hot fluid is less compared to the temperature of the hot fluid. So we are putting a negative sign. So now hot body, that is equal to, so heat released by the hot body is equal to this one. So dTh is kept it on side and others are taken the other side. So now we are taking this dTh minus dTc, and this can be called as d theta. So dTh minus dTc is equal to this one minus this one. So we have written in that fashion, and then this is called as d theta, and here dq, u we know u is equal to, q is equal to ua theta m. Q is the heat transferred through an area A, but here we are considering a small area dA. So a small heat dq will be passed, and that will be dq is equal to u dA theta m, ua theta. So that we are putting that here, u dA theta. So now this mhch, for this we can make a substitution, like we know if we are considering the whole hot body, then for this hot body temperature changes from Th1 to Th2. So heat released will be Q is equal to mHch Th1 minus Th2. For the cold body, the temperature changes from Tc1 to Tc2. So the whole heat released will be mCcc Tc2 minus Tc1. So if we are making those substitution there and rearranging it, we are able to get this theta m, that is equal to theta 2 minus theta 1 by L1, theta 1 by theta 2. So this is for this parallel flow. Now, if we are looking for counter flow, that is, if this is a counter flow means hot fluid is moving like this and cold fluid will be moving somewhat like this. If that happens, that is for a counter flow, what happens is here there will be a negative sign. Here there will be a negative sign. So here there will be a negative sign. So what happens is at the end, so in these all things there will be change. Here, look, here there will be a negative sign. So a negative sign will come here too. So because of that, here there will be theta 1 minus theta 2. This is the difference for counterflow. So counterflow we will do it. So this is logarithmic mean temperature for the parallel flow. First step is just this is considered later. First step is the heat absorbed by the hot fluid, that is equal to minus mHch dTh, from which we should take dTh. Then heat absorbed by the hot fluid, mCcc dTc, from which we should take dTc. Then dTh minus dTc, that is equal to this one. So just to say that mHch and mCcc, we can substitute an equation from here. Then just say Q is equal to UA theta m. So dQ is equal to UDA theta. Substitute that and just rearrange and let us write this equation. So